So in our next section, we're going to look at some of the additional enhancements for spanning tree that Cisco introduced into the protocol. And then later this afternoon after lunch, we're going to start talking about the newer standard, the rapid spanning tree protocol and the multiple spanning tree protocol that fix some of the design issues that were inherent to the original version. Now, as I mentioned before, the first implementation of spanning tree was defined by 802.1d, which is sometimes considered the common spanning tree, or the CST, because it means that if you have multiple VLANs, you still have one copy of spanning tree or one instance of spanning tree that is going to be used for all VLANs. The original problem with this is that it didn't allow you to change the path selection, or what we sometimes call the traffic engineering, of the layer 2 Ethernet LAN to be different for one VLAN versus another. And this is what Cisco's first extension of spanning tree was, which is called per VLAN spanning tree, or PVST. Where the idea behind this, it was a Cisco proprietary extension for it that says you're going to run multiple copies of the process, multiple copies of spanning tree, or multiple instances. And you do this on a per VLAN basis. The idea behind this is that you can do traffic engineering, or you can change the path selection on a per VLAN basis. They also came up with some additional convergence enhancements, where the problem is that if your link goes down, by default it's going to take you at least 30 seconds, or in some cases 50 seconds, to figure out that there was a change in the network, and then in order to recalculate. Specifically, these had the names of different features like port fast, uplink fast, and backbone fast. They're used for different types of failure scenarios. We'll look at some examples of these here, specifically what they do. And these enhancements were called a per VLAN spanning tree plus, or PVST plus, where the idea behind this is that it allows for interoperation with common spanning tree. It uses a pretty complex tunneling technique. A lot of this is outside of our scope for it. If you do want to get some more information on this, there's a detailed write-up on our blog that is per VLAN spanning tree plus explained, that goes over the different tunneling techniques of how basically the Cisco per VLAN spanning tree is tunneled inside of the IEEE defined MAC addresses. The specifics of the process are really not inside of our scope. But the idea for it was that you could have a case where you have a Cisco switch running per VLAN spanning tree, trying to get to another one, but in the middle you had some network that's running the legacy common spanning tree, and that was what the interoperability was. So the plus means that it's extending it to essentially tunnel over the common spanning tree network. But in our case, mainly what we're dealing with in per VLAN spanning tree is first the enhancements to do the different path selections. That instead of selecting one root bridge overall, we're going to do this on a per VLAN basis. Whereas I mentioned before, the root bridge election is going to be based on the priority value. If there's a tie in the priority, then we look at the system ID extension and the MAC address. But the idea with per VLAN spanning tree is that we can change this value on a per VLAN basis. So we previously had VLAN 1, which we were choosing as switch 1 was the root bridge. If we were to have a second VLAN, we could likewise go to the network, and let's say that we have VLAN 2. And if the other switches agree that we are running VLAN 2, if we look at the show VLAN output, since from yesterday's configuration the switches are still running VTP, the VLAN trunking protocol, when I created the VLAN 2 here, it should have been advertised to the other switches. Likewise, we look at the show VLAN. Switch 2 knows about VLAN 2, as should switch 3 if we show VLAN. So this now means that for this newly created VLAN, we're going to have a separate root bridge election, and we're going to have a separate root port election. Previously for VLAN 1, when we look at the show spanning tree for VLAN 1, switch 1 was configured to be the root bridge, and this was accomplished by lowering its priority value, where the lower values are preferred. If we now look at the show spanning tree VLAN 2, this is going to be a separate unrelated topology, where switch 1 was the root for VLAN 1, but it's not the root for VLAN 2, This is now falling back to that default calculation, which is based on the MAC addresses of the 4 switches, where switch 4 still has the lowest value out of the 4 of these. So we would see that for any newly created VLANs, that switch 4 is always going to be the root bridge. The same would be true if we configured VLAN 3 and show spanning tree VLAN 3. Since this address is the same for each of the new VLANs, the only thing that's changing is essentially the system ID extension. The path selection for the first VLAN is going to be the same as all of the later ones. But the idea is that we have the flexibility to change this if we wanted to. We could change the priority separately for this instance. We could also change the individual path selection for the instance, which means that we can control not only the bridge priority, but we could change the port attributes like the port cost or the port priority, which ultimately decides how are we going to build the topology to reach the root bridge. Where again, the overall idea behind this is that depending on what the physical layout of your network is, maybe you have web servers in VLAN 10 and you have your mail server in VLAN 20, where I may want the VLAN 20 traffic to be using switch 3 as the root, but for VLAN 10 I want switch 2 to be the root, because that's more natural based on however I have the network physically configured. So it would be the same type of configurations as we did before, changing the bridge priority or changing the port cost, the port priority. The only difference is that we're doing this on a per VLAN basis. So I'm not going to go through all the examples of this, but if we look at the resulting configuration, the only difference syntax-wise is that you're just referencing the VLAN number when you're changing the bridge's priority or when you're changing the port's cost. So just keep in mind that on the Cisco switches, by default, you will be running this version, which is the per VLAN spanning tree, so you have the separate calculations on a per VLAN basis. This also means that as you start to scale the network, you can actually run into some problems when you are running too many copies of spanning tree. So if I were to have theoretically 1,000 VLANs in the network, it means you have 1,000 different BPDUs that are being advertised every 2 seconds. And it means you have 1,000 different root bridge elections, you have 1,000 different path selections. So it has its design advantages, which is that you can change the path for the VLANs separately, but it also has disadvantages where it makes the network a little bit harder to scale. So we'll see that when we look at the next iteration, which is the rapid spanning tree protocol and the multiple spanning tree protocol, there was a new standard defined that took advantage of Cisco's enhancements, but made it a little bit easier to manage. And we'll talk about that later this afternoon.
Is there a recommended amount of VLANs to not exceed before you start seeing goofy things?
A lot of times what you would see in today's networks is that the VLAN should actually be constrained just to your access layer. And basically, the result of this is that you don't even need spanning tree to begin with. So if I have host A that's trying to reach host B, when I connect to my distribution switches, you basically have 2 options in the design. This could be a layer 2 interface, or this could be a layer 3 interface. If it's a layer 2 interface, it means that for A to get to B, they're going to have to use layer 2 switching. So it means that you're extending the CAM table between the switches, which means that you're extending the spanning tree domain. But if we were to configure these as native layer 3 interfaces, where there's an IP address on this side, there's an IP address on this side, and then you run a routing protocol, like you run OSPF or EDGE-RP, in this case, you don't have the extra convergence time of spanning tree, you just have your layer 3 routing protocols. So you can do it either way. There's some good design documents on Cisco's website that talk about this. And I believe it is the routed access layer is the document. And this is part of that high availability network design guide that I mentioned yesterday. This one says high availability using the routed access layer with eIGRP or OSPF. It basically means that you can eliminate spanning tree and then you don't have any of these problems to begin with. So since the switches can basically route layer 3 as fast as they can do layer 2 switching, essentially, then you can just use the routing protocols and then kind of get away from this, this problem.
But if you're running say you're running a collapsed core and you're doing layer 2, the VLANs would have to reside on the access layer, wouldn't they? Or would they reside on the core?
It depends on how far you extend your layer 2 domain. In today's networks, it gets a little bit more complicated because some of the applications require layer 2 reachability as opposed to layer 3 reachability. Like when you look at certain data center environments, let's say you're doing something like virtualization, where you're trying to do like the separation of your CPU resources and your memory resources versus the storage. Like VMware calls it the, what is that, when you change the virtual machine between the physical boxes, the vMotion. The problem with vMotion is that it's a layer 2 feature. That if your servers aren't directly basically layer 2 attached to storage, you have issues when you move from one physical resource to the other one. So originally it was that the networks were using this layer 2 design end-to-end and moved to layer 3 routing. But now in a lot of the data center environments, it's actually moving back the reverse way. So now it's introducing a lot of these additional layer 2 issues like spanning tree. So there's some additional ways that you can solve it. There's new protocols that have been invented to fix some of those issues. One of them in the data center environment is called OTV, which is Overlay Transport Virtualization. This, of course, is going to be outside of our scope for CCNP, but this would be where a lot of the data centers networks are moving towards today. This is one of the features of the new Nexus 7000 switches, where basically you're trying to bridge the layer 2 network over like a multiple layer 3 hops. And you run into this problem where you need spanning tree in order to do the path selection. Otherwise, you end up in loops in the network. So it really depends on the overall network design. If you have an enterprise network, a lot of times nowadays it's easier to do this, just to use routing to solve the problems. But in data center, it becomes more complicated because the applications, sometimes whoever's writing the applications will just say, well, put them on the layer 2 network and then let the network guys worry about that. But then they don't realize that there's all sorts of other design considerations that come into having a flat layer 2 network versus a layer 3 routed network. But talking within the scope of just layer 2 networking, some of the enhancements that Cisco originally came up for with this, first of which is the port fast feature I mentioned a little bit in our last section, which the idea behind this is actually twofold. That when you connect an end host to the network, we have to go through what's known as the forwarding delay, where we start in either the disabled state or we start in the blocking state, and we have to transition from listening to learning before we can go into forwarding, because the switches are basically trying to figure out what does the network look like. And we're using this to build the layer 2 CAM table. But the problem is that for devices on the edge of the network, there's really no reason that they should wait for this delay. And also we have that other limitation that when you connect them to the network, you generate this topology change notification, or the TCN. And we can actually see this on the switches, where in the current network, we have router 1 connected to switch 1. This is part of VLAN 1. For VLAN 1, switch 1 is the root bridge. Then I also have router 4 and router 6 configured down here, where these devices have the addresses 10.0.0.1, 10.0.0.4, and 10.0.0.6. Right now, configuration-wise, router 4's interface is disabled. So it's not part of the network yet. It's not part of the layer 2 switching topology. From router 6 to reach router 1, we should have basic layer 2 connectivity. And again, if we were to trace between the destinations, they look like they're one hop away. So we're using layer 2 Ethernet to reach each other. In the core of the switch network, when we look at the show MAC address table dynamic for VLAN 1, we see that we know about the MAC addresses of router 1 and router 6. And these are going to stay in there for about 5 minutes by default, unless we hear traffic coming from those hosts, in which case it's going to keep getting refreshed. And these MAC addresses are going to stay in there. If we look at on the root bridge, the debug spanning tree, let's say debug spanning tree all. That should take care of it. And what I'm going to do is to say logging console 6 and logging buffered at level 7, because you can see this is a lot of output here. And to cut down on this a little bit as well, what I'm going to do is, for right now, is just delete the other VLANs. So I'll say no VLAN 2 to 1000. That's going to get rid of those other BPDUs. If we look at the show log output, right now the console is logging at level 6 for informational. It basically means those debug messages are not going to appear on the console. They're going to the buffer, which means that when I show log, they're going to appear here. And it's going to have to be less than that. This is too much information. What I want to see then is, let's try events. So on router 4, which is attached to switch 4 physically, I'm going to enable this interface. So in global config, for the interface, no shutdown. When we look at the result of this on the root bridge and now show log, we should see that the downstream switches are going to generate, and let's start this over. Let me clear the log out. Debug spanning tree events is on. Then let's try disabling that interface of router 4 again. The key what's happening is that this link from the layer 2 switches point of view, it's going up and down. This is causing a change in the state of spanning tree or the role of the port. We could see when the link went down, switch 1, who is the root, it says a topology change notification was received on the interface. This is the link here that's facing down towards that bridge. So a TCN, a topology change notification, came in this interface. The same is going to be true once this interface comes back. So this would be the equivalent of someone plugging their cable into the network and unplugging it. Switch 1 should receive another topology change notification eventually when the port changes its state. What this is doing is to try to tell the rest of the network to flush out the CAM table or delete the MAC address entries that you have. So if we now go to the switches and look at the show MAC address table dynamic for VLAN 1, we would see that these MAC addresses are eventually going to get deleted unless router 1 and router 6 are exchanging traffic, or unless router 1 and router 4 are exchanging traffic. And the problem is you wouldn't normally want this every time a host plugs into the network, that you flush out the CAM table and then the switches have to re-flood the traffic everywhere. So this is going to be one of the features of running the port fast, that not only do the end hosts not have to wait for the forwarding delay, when that link changes states, the switch is not going to generate this topology change notification. But if we look at it as it stands now, And let's say that router 4 does a ping to router 1. And we send a bunch of pings with a timeout of 1 second. If the link that is attached to router 4 flaps, so the link goes down, and then the link is going to come back up, even though the link is now active, router 4 is going to have to wait for this forwarding delay. And we would see this on the switch when we look at the show spanning tree for VLAN 1, that this interface, now it's in forwarding. Previously, it would have been in listening and learning. So eventually, after this timer expires, then 4 is going to be able to send traffic. And these dots here, it's showing where it was dropping the packets. Switch 1 during this period also received the topology change notification, which tells the other switches then to flush out their MAC address tables. But again, typically you would not want this. So on the ports that go down to the edge of the network, we would say these are running in port fast state. The switch warns you when you turn this feature on that it should only go to hosts, or it should only go to ports that are going to single hosts. Don't connect it to hubs, to switches, to bridges, etc., because you can cause a loop in the spanning tree network. The reason why is that you're not waiting for that listening and learning delay in order to start forwarding traffic. You just immediately start sending the packets. Eventually, the network would sort itself out. These become temporary bridging loops, but you always want to avoid this with layer 2 spanning tree, because the utilization of the switches could get out of control, and then spanning tree wouldn't have enough CPU resources in order to actually do the calculation. And basically, you could take the network down by doing this. But as long as this port goes to an end host, then it's not going to be subject to the forwarding delay. It's not going to cause any of these problems. So now if I were to disable the interface, we see that router 4 starts to drop packets, because right now the link is disabled. When I re-enable it, we should see almost immediately that the link starts to be able to forward traffic, because now it doesn't have to wait those additional 30 seconds, which is the forwarding delay. Additionally, on switch 1, we didn't receive a new topology change notification. So the aging time for the MAC address tables are going to be left the default values. Question?
Can you disable a spanning tree on the switch or on a VLAN?
You can disable it globally. You cannot disable it on a per port basis, though. So I could just say no spanning tree VLAN 1. But the problem is, since there are physical loops in the network, this would basically crash the switches.
But if you do that, then you don't need to do port pass if there are no other switches connected to that switch. Would they still need to do to configure port pass on the ports?
If spanning tree is off, no. So if your network had no physical loops, you can do this. This is fine. But as soon as someone plugs an additional cable and you form a loop topology, then it's going to take down the switches.
I was not able to disable spanning tree on a 3560s V2 and the X series. I don't know, for some reason the PVST stayed always on.
Well, let's try it. Let's see what happens. Now there's no instance. It could be for that platform. It doesn't allow you to do it. But again, normally you wouldn't want to do this. So as soon as you create the VLAN, it automatically starts an instance of spanning tree. You can also see when I was looking, this is the debug spanning tree events. You can actually see the transitions between the port states. And if I were to have the timestamps on, if I said no spanning tree VLAN 1, and let's see the other config that I have right now. Show run include spanning tree. I changed the timers as well. Let me set these back to the defaults. When spanning tree is enabled, we should see that, and actually can't see that based on the timestamps. Let me do this. Let's say service timestamps for debugs. I want the local time, so the date time, and the millisecond. So once spanning tree is enabled, it says that at 42 seconds after, the port went into the listening state. We should see at about 57 seconds, give or take, it now moves to learning. And then 15 seconds from here, it should move to forwarding. Because this is the addition of the 15 seconds for the listening delay and the 15 seconds for the learning delay. This is normally what the convergence time is. So at 12 seconds afterwards, now it goes to forwarding. So you can actually see what the calculation is if you were to look at this debug. The problem is in a large network that this runs on a per VLAN basis. So if I were to say on one of the switches, VLAN 1 to 1,000, once this is advertised, and it says I have a limit of 128 instances, for each of these VLANs, it now has to go through the calculation. So if we look at these switches in the middle, let's say like show proc CPU history, it's going to be a lot of utilization to try to calculate this. So this is one of the disadvantages of running the default value, which is the per VLAN spanning tree. We'll see that there's a way that you can fix this, that you can have the flexibility of doing the path selection for the different VLANs, but not have to run one instance for every single VLAN that you create. But again, this was their first enhancement, which is the port fast. It says two things. You don't have to wait for the forwarding delay, and don't generate the topology change notifications. The other one is called uplink fast. This is used when your directly connected root port goes down. It's an optimization that if your connected root port goes down, you can immediately transition to an alternate port and send the MAC address table out that new interface to try to immediately reconverge the rest of the network and switch over to the new link. Like if we were to look at the case where we have now, where switch 4 is going in this direction for the VLAN 1 traffic, and this is going between router 4 and router 6 and 1. When we look at the show spanning tree for VLAN 1, it says my root port is 16. So I'm sending traffic in this direction. The problem is that if this port goes down, we see right now router 4 is doing those pings. There's no problems in the topology. If this port goes down, fast Ethernet 16, even though it's directly connected to me, I know that I should start to recalculate. Router 4 is still going to drop packets until we go through the listening and learning delay on this interface. So it's going to take a long time to converge if there's a physical failure in the network. Where uplink fast says that I'm positioned on a switch that I know I have one primary interface and one backup interface. Or from the perspective of spanning tree, what we call an alternate port. If uplink fast is on, switch 4 is going to do two things. It's going to try to take itself out of the root bridge election. So it tells the other switches, don't elect me as the root. And the reason why it's kind of violating the normal convergence techniques, that you're supposed to wait for this listening and learning delays, it's going to try to skip over that. So if we look at router 4, eventually it reconverges. But it's about 30 seconds, give or take, for it to do that. But if switch 4 is running the spanning tree uplink fast feature, and it may be, let's see, spanning tree uplink fast. If we now look at the show spanning tree for VLAN 1, it does a couple things. It raises its own priority value, which tries to remove it from the election process. Because everyone else, by default, they have 32,768. If I set mine higher, I set it to 49,152, which is here. It means I'm less likely to be elected to root bridge. Additionally, it raises the cost values of the interfaces. It's going to add 3,000 to all of these connected links. So it's also preventing other switches in the network from using it as transit, where if I were to have VLAN 1 here and VLAN 1 here, when switch 3 does its path selection, it's less likely to go this way because it has 3,000 plus whatever the default costs are, like 3,019, versus 19 and 19 here. I would just exclude this because this is a higher cost path. So it's trying to get no one else to use it as transit, no one else to use it as the root bridge. But now the key is that the switch is going to know once this alternate link is back available, which is fast Ethernet 16 here. If we look at the show spanning tree for VLAN 1, switch 4 is going to know that one of these links is alternate, one of them is the root port, where we should see that once this goes through its initial convergence, this port should be preferred because it has a lower cost value. So the switch is saying I have two possible ways I can get up to the root. I can use my primary root port, or I could use my alternate port. Since I'm running uplink fast, if this directly connected root port goes down, I immediately transition this one to the forwarding state and then advertise my full MAC address table out that new interface to try to update the rest of the network. So if we look at router 4 now, we can see that it's sending packets, everything is fine in the communication. If this directly connected interface goes down, so fast Ethernet 016 right now, this is the root port. If I shut this down, from router 4's perspective, it's only 2 seconds of convergence. So it's a little bit faster than the default, which is going to be somewhere maybe 30 to 50 seconds, depending on where the failure happens. So the key for this one is that if it's your directly connected root port and that goes down, you can switch over to the new alternate one almost immediately.
Which interface did you put that uplink fast command on? Was it 16?
You put it on globally. Oh. So you simply turn the feature on, and then it knows basically based on the BPDUs that it's receiving in the interfaces when it looks at the show spanning tree VLAN 1. And it would actually look at the detail. Behind the scenes, it's going to look at what are the interfaces that I'm learning the root bridges BPDUs, which basically means those are multiple possible paths to get to the root bridge. I choose one of them as primary. Then if the primary goes down, I can immediately switch over to the backup one, to the alternate port.
Put on switch 4, right? So why would you not want to use that?
We'll see why later.
Would you put that on just one switch and then spanning tree would just push it out, or do you have to configure that on every switch?
You have to configure it on every switch. But the problem is you can only put it at either your access layer or your distribution layer. You would put it on someone that is not transit for other portions of the network. Because you're essentially violating the normal convergence rules that if I have two access switches that have links to distribution switch 1 and distribution switch 2, you would want to run uplink fast on this switch and this switch. If you run it here, you run the risk of maybe traffic from another portion of the network going this way. It really depends on the topology. There's some strange cases you can get into, and you actually can cause a loop in the network temporarily while it's converging to the new links. So traditionally, it's used just at the access layer where you have two links to the rest of the distribution, to the uplinks. So it's just that one command to use, which if we show run include spanning tree uplink fast. The other one is kind of a more obscure case, which is known as backbone fast. This is to try to detect an indirect failure in the network, where an indirect failure is based on the maximum age timer. Where the case that this is trying to prevent is that if switch 1 is the root bridge, and we're looking at the path selection from this bridge's point of view, switch 4 at the bottom. Right now, I have configured this as my root port. This other one is in the blocking state right now. The problem you can run into with the original calculation, the original legacy spanning tree, is that when the BPDUs go out in this direction from the root downstream, these are going to be going out every hello interval, which by default is 2 seconds. The root bridge also tells the other switches that the time that you should hold on to these, the maximum age, is 20 seconds. If the BPDU goes above 20 seconds, it means that there was a failure somewhere and you should start to reconverge. Now with uplink fast on switch 4, we knew that if there was a physical failure here, we should immediately start to reconverge in this direction. But the problem is that if the failure happens here, switch 4 doesn't actually tell that downstream switch. It has to wait for the max age to expire. It has to wait 20 seconds before it can start to recalculate in this direction. So you'll see that depending on where the failure happens physically in the network, you have multiple possible cases for convergence. Where best case scenario by default, you're going to get somewhere around 30 seconds. Worst case by default, you're going to be somewhere around 50 seconds. So this is what they came up with as kind of a temporary solution for this, where when the backbone fast feature is on, there's a new layer to keep alive that goes between the switches that they advertise this capability to each other. And basically you have to enable it everywhere in the network to make sure the switches agree on this. The idea is that if this link goes down, and this was our root port down here, if this link goes down, switch 2 is going to start advertising a worse cost to the root bridge, because it no longer has this path in order to reach the root. So it's going to advertise some high cost value or some high priority value that previously it was excluded from the topology based on this because someone else had a better priority to begin with, or someone else had a lower MAC address to begin with. The key with backbone fast is that if you hear these advertisements, a worse cost, start to come in your root port, it tells the switch that a failure happened somewhere upstream. So it didn't happen directly on my connected interface, it happened on someone else's interface multiple hops upstream. So you basically immediately set the max age to 0 and then go through the listening and learning phases again. The problem with this one is that it only saves you that maximum age timer. So it gets your convergence from about 50 seconds down to 30 seconds, but it's still fairly slow in terms of today's networks. But again, configuration of these, they're pretty straightforward. You would say spanning tree uplink fast in global config. At the interface level, you can say spanning tree port fast On some of the newer versions, there's also a feature of this where you can say spanning tree port fast default in global config. And the switch is automatically going to figure out which interfaces you should run port fast on and which ones you shouldn't. And it does this based on interfaces that receive BPDUs. Because if we figure that the spanning tree network or the switching topology is going to look something like this, where you have the root, and then you have, eventually you connect down to your access ports, or your access switches, and then you go down to your end hosts. So here we have A, B, and C. The BPDUs start at the top of the tree. They start at the root. They move in this direction. From this access switch's point of view, it means that BPDUs are not coming in on these interfaces. So if we were to look at a counter like on switch 4 and say, show spanning tree interface fast Ethernet 4 detail, I'm sending BPDUs, but I'm not receiving them because there's no device on the other end of the link that's running spanning tree. So basically, the switch makes this assumption then that if you're not receiving BPDUs, put that interface into port fast state. But at a later time, if you start to receive BPDUs, it means someone is running spanning tree. So in that case, you can't run port fast. So it essentially allows the switch to automatically control what portion is the edge of the network and then what portion goes up to the switches. So a lot of times in today's layer 2 switching configurations, this would be what you want. That spanning tree would be on, or port fast would be on by default, and then the switch is automatically going to figure out which interfaces you should run it on and which interfaces you shouldn't run it on. There's a couple good documents on these other features that I mentioned. This is one here. We'll talk about this a little bit later. But if you find any of these documents on Cisco's website that start with the keyword spanning tree protocol enhancements, this is where they talk about some of their changes that they made to per VLAN spanning tree plus. But in our next section after lunch, we're going to talk about the rapid spanning tree protocol. This is what fixes the problems in the legacy algorithm and then in the per VLAN spanning tree protocol. So this was standardized quite a while ago at this point with 802.1w. If you are going to run spanning tree, this is really what you should run because it automatically fixes a lot of these design problems.